All right. Is the recording started?
Yep, good to go.
Perfect. So thanks everyone for joining the third infrastructure working group as part of the Connecticut Hydrogen Task Force. Again, some meeting logistics, quickly going through them. Please mute your microphone unless you're speaking. If you'd like to speak, feel free to raise your hand and we'll call on you as we go through the slides, and then there'll also be a Q&A portion at the end. You're also welcome to ask questions in the chat box, and we'll try to get to them in real time or save them for the Q&A period. A reminder, this meeting is being recorded, and so please, when you're talking, please state your name for the record, so that the record will know who is speaking at any given moment. And a quick run through of today's agenda. So again, we'll do some welcome and introductions just so everyone knows who's on the call, introduce anyone new. Looks like we have a relatively small crowd today, so might need less than 10 minutes for that. But then we'll go into some discussion on potential hydrogen infrastructure that would be required to be developed in Connecticut, looking closely at, or more closely at, some of the ancillary infrastructure that's required to transport hydrogen and store hydrogen, as well as some notes on the safety and supply chain components of developing a hydrogen infrastructural system. And then we'll have time at the end for discussions and some discussion of next steps. So quick reminder of Strategen's role. I won't go through this in detail either. This has been part of a number of other slide decks, but just as a reminder for the role that Strategen is playing in the overall task force proceedings. And then want to hear a little bit more from you all. We'll do a quick round of introductions. I'll start. I guess everyone kind of perhaps has been in a call where I've introduced myself before, but in the interest of comprehensiveness, my name is Colin Smith. I'm a senior consultant at Strategen on the commercial side, doing a lot of work with different efforts to evaluate and scale up clean hydrogen technologies. I'll pass it off to Nina next, and then we'll go sequentially down the list of attendees from there.
Yeah, hi, so I'm Nina. I'm a senior analyst with Strategen, and I've been supporting Colin on the infrastructure analysis and research. So I guess next would be Anna.
Hi, I'm Anna McMonigal. I am with Conservation Law Foundation here in Connecticut. I am a staff attorney, and I'm here on behalf of Shannon Lawn. And I'll pass it to Samantha.
Hi, thank you. I'm Sam Danowski, she, her. I'm the State Director of Sierra Club's Connecticut chapter.
So next we can move to Nikki.
Hi, good afternoon. My name is Nikki Bruno. I'm the Vice President of Clean Technologies in Eversource's gas business. Good to see you all.
And Sarah.
Good afternoon, Sarah Harari. I am the Associate Director of Innovation and Senior Advisor to the President at the Connecticut Green Bank.
Sridhar.
Hi, I'm Sridhar Kanuri, Chief Technology Officer for High Axiom.
And Trent.
Hi, I'm Trent Moulter. I'm founder and CEO of Skyr. We do hydrogen generation, separation, and compression.
Great, and then Becca.
Yeah, hi everybody. Becca Treat, Senior Policy Advisor, Connecticut D.
Awesome, and that should be everybody. If there's anyone I missed, feel free to speak up. All right, Colin, I think you're good to go ahead.
So thanks, Nina. I'll continue through the presentation then, but great to meet you all. I see we have quite a strong bench of expertise here in the infrastructure realm, so please feel free to speak up in the discussion section with any thoughts or additional facts you may have to extend on what's presented here today. A quick overview of the working group schedule. We're in November right now, which is the second to last working group that's scheduled. The next infrastructure working group will be December 19th, so about 1 month away. Great, and now we'll get into the contents of the meeting. Looking first at some of the auxiliary infrastructure that is required to transport and store hydrogen beyond just pipelines and electrolyzers. So hydrogen is a very light and not particularly dense by volume gas. When it's produced, it's generally produced at very low pressures, 20 to 30 bar. It must be compressed to roughly 200 to 500 bar to be economically transported as a compressed gas. So one of the reasons why compression is so important is because it would just be infeasible to transport hydrogen at lower pressures. You wouldn't be able to get enough hydrogen on a truck in order to make it worth or make it feasible to kind of move it from one point to the next. And so hydrogen is almost always compressed if it's transported in a pipeline, for example, and also for short distances, less than 100 miles, compression could be feasible for truck transport. Hydrogen's energy content by volume is roughly 1/3 that of natural gas, so it requires about 3 times as much space for hydrogen to hold the same amount of energy, which is relevant for hydrogen that's blended into the gas system. You can blend a higher percentage of hydrogen by volume and not have quite the same level of energy available. And so, additional work on managing compression in these systems is important to ensure that you're getting the same level of energy outs when using hydrogen in pipelines, either with natural gas or on its own. Similarly, when hydrogen is used as a transportation fuel, there's differences in energy and volumetric density compared to gasoline. Hydrogen is a very energy dense molecule in terms of mass, mainly because it's a very light molecule. And so because of this, it's in terms of the weight of hydrogen that you're carrying around, the amount of energy you're getting from that particular transport application is pretty good compared to gasoline. However, on a volume basis, liquid hydrogen is still less dense than gasoline on an order of 4 times less. And so that's also relevant when putting together transport applications or using hydrogen in transport applications and storing it on site. All that is to say, it's very important to be able to incorporate the cost of compression, the need to compress hydrogen when looking at the cost of using hydrogen in the economy. These costs generally run from a half to 2/3 of the total cost for compression, storage, and distribution, which equates to around $1.10 to $1.50 per kilogram of compressed hydrogen. And so that it can be a relatively significant cost adder when you're talking about compressing hydrogen to move to storage, to move through a pipeline, or potentially to move on a truck.
This is Sarah. I want to make sure I understand the what you just said, which is that regardless about whether it's being transported or stored to use on site, you'd need to compress it either way.
Yes, yeah, that's a good summary, Sarah, and my apologies for being not completely direct about that. But yes, compression is required for almost all applications of hydrogen, just because when it's produced at such a low pressure. It really is necessary to include the cost of compression for almost any application of hydrogen that you're considering.
So it would need to be compressed even if you were using it right away.
Most likely, unless it's coming directly. I mean, I'm sure there's a configuration you could develop where you completely avoid the need for compression. But even if you had a short, a relatively short distance pipeline to get from the electrolyzer to the end use that's on site, you would likely still need to include compression.
The hand from Nikki and then John.
Thanks.
Yes, go ahead, Nikki.
Colin, I just was curious, are you working with certain OEMs or other folks to kind of verify that, or where is that information coming from? Do you have that handy?
I'm happy to send out the sources we've been using after the call. I don't have them on hand. That said, they are based on our own research at this point, and there's definitely, I think, potential and good reason to validate these with some of the OEMs that are part of this working group. So I agree, Nikki. I'm happy to send you the sources and would really appreciate your insight to make sure that we're looking at the right information.
Thank you. That'd be great. Thanks.
Yes, of course.
I just wanted to, reinforce what you said, that it's harder. Hydrogen's so light, it's hard to get it anywhere. If you put it in a truck, there's not very much of it. If you put it in a pipeline, it doesn't carry that much energy per volume, not as much as natural gas. So that's a downside. The upside is that when you burn hydrogen, I think I didn't do my numbers just before this, but it takes less air. So in any engine, you have to compress the air, but not the gasoline. In this situation, you wouldn't have to compress as much air, but you'd already compressed hydrogen. So there's a compensation there in the context of an engine.
Thanks, John. Yeah, as you can see, there's a lot of technical components to transporting hydrogen that, it's a very different gas, and that means there's a lot of different considerations that change the way that it moves and can be used. As another example, hydrogen is also, I believe, less viscous than natural gas, and so it actually moves through pipelines quicker because there's less friction. And so you may be getting less energy delivered in a unit on a unit volume basis, but the flow rate can be faster. And so just another example of some of the technical features of hydrogen and how it differs from natural gas. And maybe the upshot is that none of this is really precluding the use of hydrogen in most of the applications that we're talking about. It is more just an example of some of the considerations that equipment manufacturers and OEMs and infrastructure developers have to take into account when they're developing this type of infrastructure, and also providing additional context around the cost component, which is probably the key takeaway here. I'd say really what we're trying to understand is how much do these additional auxiliary infrastructure components add to the cost of hydrogen that the final customer sees. And these numbers here, $1.10 to $1.54, are kind of general numbers taken from the literature. I think as Nikki mentioned, there is a lot of opportunity to refine those numbers through conversations with OEMs. And so, these numbers aren't going to be directly lifted and put into our modeling efforts, but as we kind of refine those estimates, they'll help us create a more complete picture of the price by which hydrogen could be delivered to end users in Connecticut.
Hi, this is Sridhar Kanuri. I have just a quick comment on compression and the discussion that happened before. In almost all the cases where you're using electrolysis for generating hydrogen, I'm at least pretty positive that there is not a need in that location, because you're converting the excess energy to hydrogen to be used in somewhere else. If that is for energy conversion, you might as well use the energy there. So that's, I think, one of the reasons why you need to compress and transport it to a different location or use it at a different time. Second is there are applications where, for example, we had an example with a petrochemical complex where they improved their processes and they were left with excess hydrogen. And in that case, we were able to put 50 megawatts of our fuel cells there to consume that hydrogen because it was just going for waste. So such a scenario, you don't need to compress hydrogen. But in other cases where curtailed energy is used to have hydrogen as an energy carrier, you do need to compress and transport it.
Thanks, Sridhar. That's a really good example for you, Sarah, of a situation that in which you might not need compression. As you can see, they're kind of relatively niche applications where there are niche applications where you might be able to get away without compressing hydrogen, but the large majority of use cases that are generally discussed, some sort of compression is usually required.
I'll just chime in. For use in heating and combustion, low pressure is fine too, but to get it there, you need high pressure. For distribution lines to residences and things like that, in England, they're using very low pressure PVC tubing, which is sufficient. You don't have high pressure in the lines that go to the households and commercial places. So for distribution, low pressure is okay, but for getting it to the distribution, well, upstream, it must be high pressure, and what you're talking about is very valid.
Are you aware, John, what pressure they're looking at in England for distribution to homes?
I can find that out. I think it's inches of water pressure.
Okay, I'm not familiar with that metric.
It's in terms of bar, it would be less than 0.1 or something like that.
That's quite low, yeah. Well, thanks for that insight. Any other thoughts before I move on?
I think there's a hand from Trent.
Go ahead, Trent.
Yeah, just to jump in on a couple of items here. Currently, for industrial applications, it's not uncommon for hydrogen to be trucked, say, 200 or 300 miles from the point of generation to the end user. And the issue that we currently face is there's not a lot of point sources of production of large-scale generation of hydrogen. So oftentimes you'll see compressed hydrogen or even liquid hydrogen being trucked long distances. In the future, hopefully that's not going to be the case. And we might only be trucking short distances like you see here of 100 miles or less, but currently it is problematic. And the second point that I sort of mentioned is we're very fortunate here in the US in that there's a significant liquids infrastructure for hydrogen. And that's a result of the space program, which uses hydrogen as a liquid fuel. And so there are several individual liquid production sites here within the US. So certainly in industry, hydrogen is used in liquid form, particularly for users who use larger amounts of hydrogen. It's just cheaper for them to do so. Usually smaller users use compressed gas, and even smaller users use cylinders of gas delivered to them. So that's typically the distribution that you see.
Thanks, Trent. Yeah, that's helpful context for sort of the current circumstance. And of course, what we're looking at is sort of the future system that we could develop. And so like you said, hopefully in the future, we will not need to ship large quantities of hydrogen via truck, either as a gas or necessarily as a liquid. Pipelines are much more efficient forms of transport for bulk delivery of hydrogen, which is something that we discussed at the last working group meeting. which hopefully you were able to attend. But I think it's worth reiterating that point that truck delivery of hydrogen is not necessarily the optimal solution, even if the gas the hydrogen is compressed or liquefied. And so the method of delivery and transport use will have to be very closely tied to the use case.
Yep.
All right, well, jumping on to the next slide. We'll quickly discuss the topic of local storage for hydrogen. So we talked about geologic storage last week at the last working group, which is really focused on bulk storage of very large quantities of hydrogen, but you also need to be able to store hydrogen locally in order to keep it at a fueling station or keep it at an industrial site where before it's used to fuel a truck or a industrial process or whatever your preferred application is. And so some options for doing that is storing it as either gas or a liquid in all metal cylinders or other types of specialized material containers. In these cases, the gas would also need to be compressed or liquefied in order to make sure that it's energy dense enough by volume that you can store enough hydrogen economically. And this is really key for enabling the use of hydrogen in a number of applications, including stationary power, backup power applications, industrial applications, or transportation via storage at fueling stations. And so I've alluded to liquefaction of hydrogen a number of times throughout this presentation, so I wanted to address it directly. Another way of increasing the volumetric energy density of hydrogen to make it more easy to transport or store is to liquefy it, which is a more energy intensive and expensive process than compression, but is often preferable, particularly if you're looking at delivering hydrogen by truck over longer distances. So usually if you're traveling with hydrogen over 400 miles, liquid hydrogen is almost always the most economic option for storing that hydrogen on board the truck. And like I said, liquefaction is a more complex process. Consists of 3 separate sub-processes, the first of which is compression. So you have to first compress the hydrogen, then cool it to very low temperatures, which has corollary energy requirements and costs associated with it, and then expansion to a usable form of liquid hydrogen where that can be stored. So as Trent mentioned, there is existing liquefaction infrastructure in the US. And there's been a substantial amount of research on the economics of industrial liquefaction. This research focuses on relatively small liquefaction stations, around 6,000 kilograms per day of hydrogen, or large installations of around 200,000 kilograms could be some of the largest potential installations. And the estimated capital costs for these can range significantly from 30 million to 490 million. But I think the important takeaway here is that there's often economies of scale to liquefaction, where if you build a larger liquefaction plant, the overall capital investment will be higher, but because you're able to produce more hydrogen or liquefy more hydrogen at facility, the cost per kilogram of hydrogen liquefied drops. So at a capacity of 27,000 kilograms today, which is a somewhat typical capacity for the current fleet of commercial liquefiers, you could expect the capital contribution of the liquefier to be around $1.40 per kilogram. Though with electricity and other costs, that can get even higher, up to $2.75 per kilogram. And so this is a significant expense as well, and one of the reasons why even a low delivered cost of hydrogen or a low cost of hydrogen at point of production doesn't necessarily mean it's economic for use cases where it might need to be liquefied and transported over long distances. But again, this is information from a literature review and not necessarily specific to the use cases or geography of Connecticut. And so these estimates will be refined as the analysis as our analysis continues.
It looks like Sarah maybe has a question or a
Yep,
comment.
go ahead, Sarah.
Yeah, so I guess I'm curious about if you can talk a little bit, Colin, about how this is tying into the sources and uses group. Like how much are we allowing the ability of storing and transporting the hydrogen to influence what are the selected recommendations for sources and uses? If it feels like liquefaction and transportation is not short-term viable in Connecticut, would that rule any of the sources and uses out? I guess it's another way to ask the question.
That's a good question. And I think it's good to foreground that discussion a little bit rather than waiting towards the discussion on next steps at the end, because it is important to kind of understand and contextualize why we're talking about these costs, why these are important. And the approach that you discussed is one possible way it could be applied, determining whether or not liquefaction or compression is viable in Connecticut is one way to look at it, but probably more maybe a better approach, and the one that we would propose is that we first identify through the demand assessment how much liquefaction is required and what cost that liquefaction would add to the delivered cost of hydrogen, at the pump, at the fueling station. And then that allows us to understand what additional support might be required to make hydrogen a competitive fuel from a transportation perspective, or from the perspective of the other applications, as a maritime fuel, things like that. So I know you were on the call earlier today, Sarah, when you saw the levelized cost of hydrogen estimates for producing hydrogen from different renewable energy feedstocks. And a lot of those came in around $2, $3, depending on the feedstock and the relative availability of subsidies. Yes. So imagine that levelized cost of hydrogen is sort of the base, and then you're building on that with the additional infrastructure that would be required. So with liquefaction, $2 per kilogram LCOH at point of production could increase to like $4 or $5 at the point of final delivery to a transportation customer. And I mean, that's not unique to hydrogen. Diesel also costs a lot more at the pump than it does at the refinery. And so all of these different fuels, the cost of transportation and storage is added to the final cost that the producer sees. And so what we're trying to do is kind of create, provide some context on what additional steps would be required, what additional infrastructure and costs would be incorporated into that delivered cost of hydrogen that the end user sees, and then also how we'll kind of build up to that delivered cost estimate based on the underlying LCOH and then also the additional infrastructure that's determined to be required. Does that answer your question and it overall make sense?
Yes, thank you.
No problem. Any other questions before I move on, or thoughts on what I just described? All right, in that case, I'll move on to derivative fuels. So this is derivative fuels are an area of sort of hydrogen usage and transportation that usually is more relevant for very kind of very long distance transport or use of hydrogen. But it is a way to move hydrogen over long distances. Hydrogen can be used to produce ammonia and other synthetic fuels via processes that are, in many ways very similar to the refining processes that take place at refineries in the U.S. today. And these synthetic fuels can be used directly as a fuel. For example, ammonia could be used to power a ship traveling, on transoceanic voyages. Or hydrogen could be turned into ammonia, transported over the ocean, and then turned back into hydrogen. And so that's another way to potentially transport hydrogen over long distances. For this application, or either as a fuel or as a transportation method, turning hydrogen to ammonia is a particularly promising approach because ammonia is much easier to transport than hydrogen. It's liquid at room temperature. It is relatively has a relatively high energy density, and there's also already infrastructure that exists in the world to handle and transport ammonia, as you can see from this graphic on the slide. And so it's highly unlikely that we'd be turning hydrogen into ammonia to move it from like New Haven to Bridgeport, or even New Haven to New York. But there could be opportunities to turn hydrogen into ammonia or another derivative like methanol in order to put it on ships going out of Bridgeport, or use it as an aviation fuel at the airports in Connecticut. So going a bit more, doing a bit of a deeper dive into the topic of derivative fuels, the current commercial scale method for converting hydrogen to ammonia is known as Haber-Bosch, but new methods are being developed and researched, and there may be other options, more efficient options for conversion in the future. You also have the opportunity to convert hydrogen to either methanol or synthetic kerosene, which can also be used as a fuel in the shipping or aviation industries. You can see here in this diagram the process by which ammonia can be produced by hydrogen and the constituent parts of that process. Anytime we're talking about ammonia, it's important to point out that ammonia is, a toxic substance, and so there is definitely a large need to develop more stringent safety procedures if ammonia is going to be produced and transported en masse. And those safety procedures are already well known and exist in many places across the world that already handle ammonia. And then ammonia is a major chemical input for the fertilizer industry. And so there's a lot of experience across the world around transporting or storing or using ammonia. However, that doesn't necessarily mean that exists within Connecticut today and might need to be developed, and it also means that if ammonia is starting to be produced and transported at higher volumes, that there could be a need for additional safety procedures to ramp up as well. So what does this mean for Connecticut? So where you cite different types of infrastructure is also in a lot of ways connected to the usage of hydrogen within Connecticut. So liquefaction and derivative fuel production, like ammonia, makes sense to site those facilities close to where the liquid hydrogen or the derivative fuel would be used. And so there just might be opportunities to advantageously locate it near major ports or transport routes. such as the one shown there. Obviously, a lot of other considerations. This isn't a suggestion by any means. As was just mentioned, ammonia in particular requires new safety procedures to be developed, and so there's definitely concerns about making sure that that's not near vulnerable populations or places where it could harm communities. But in terms of general siting principles, this is one thing to consider when thinking about developing hydrogen infrastructure throughout the states. Similarly, compression infrastructure would be required for pipeline transport and also for geologic storage in order to compress the hydrogen within the salt dome itself. And so if Connecticut were to connect to geologic storage via a pipeline, compression will be required for that effort as well. I also wanted to briefly touch on infrastructure safety. The safety concerns that are components of transporting hydrogen via pipeline or any other approach. So pipeline safety is one of the most salient, as pipelines, as mentioned, are one of the most economically efficient ways to transport bulk hydrogen or hydrogen in bulk. And hydrogen is a different molecule than natural gas, and the chance of embrittlement of pipelines from using hydrogen is particularly important to consider, especially in situations in which hydrogen is introduced into pipelines that are designed to transport natural gas. So specialty steels can be used to mitigate this concern, and typically once hydrogen blends in a pipeline environment get high enough, there is a need to develop a hydrogen pipeline specifically constructed from materials that can safely transport that hydrogen without risking embrittlement of the infrastructure. Hydrogen, like most fuels that we use, is also highly flammable. That's because it's very energy dense. But hydrogen fire radiates significantly less heat than comparable fossil fires, so there's less of a risk of thermal damage. It also disperses more quickly than in a lot of other gaseous fuels, and so that also helps it be a bit less risky of a fuel to move or use. Like all fuels that exist, there's risks with hydrogen that need to be managed, but they're slightly different risks than natural gas or some other comparable fuels. PHMSA currently is the primary authority to regulate the safety of energy commodity pipelines, both interstate and intrastate. These safety regulations cover pipeline design, construction, operation, and maintenance, as well as spill response. And so these are all areas of active regulation that would apply to hydrogen as well. PHMSA also regularly provides grants for pipeline safety research to inform its regulatory activities. This includes research into better or more efficient and safer designs of hydrogen pipelines that can make moving this gas a more easy proposition at scale. In terms of auxiliary infrastructure, as mentioned, the characters of hydrogen do create risks. They're not the same risks as natural gas, but there are also risks that can be managed. This includes vulnerability to leakage, the ease at which it can be ignited. And so there are various codes and standards that have been developed to outline safe practices for hydrogen handling, particularly in the case of liquid hydrogen. As mentioned, I think at the last working group meeting, hydrogen is currently used in many parts of the country, moved around by trucks or by pipeline. And so these safety regulations do in fact exist they might just need to be applied to new places as the hydrogen economy or as the use of hydrogen in the economy expands. So as mentioned, liquid hydrogen storage tanks in particular have a number of safety mechanisms connected to them, including overfilling protection, things like pressure relief valves, rupture discs, and pressure safety valves. I'm not sure if anyone on the call with more technical experience with liquid hydrogen would be interested in speaking up here. I will admit I myself am not an engineer and would love to hear insights from others on the call. But I think that the takeaway from this slide is that there's procedures that need to be put in place to effectively handle and move hydrogen around and store it, and that a number of these procedures are already well understood and implemented in other places. Right, well, moving on, I want to touch quickly on the infrastructure, the supply chain for hydrogen equipment and infrastructure. So like a number of technologies used in our move to decarbonize the global economy, fuel cells and electrolyzers require material inputs that are often scarce or not produced in America. Which creates potential supply chain concerns. The DOE has evaluated this and identified a handful of materials typically used in electrolyzers and fuel cells that are at particular risk of potential supply chain disruptions. Things like graphite, iridium, platinum, strontium, and yttrium, all of which are if not 100% imported from abroad, mostly imported from abroad. You can see here China and South Africa supply a large portion of those materials. Several other materials face moderate supply concerns such as cobalt, copper, nickel, and manganese. I think these are especially worth pointing out because these are also materials used in a number of other clean energy technologies like batteries or transmission wires. And so we've witnessed significant supply disruptions to some of these technologies because of COVID and other challenges in the global supply chain in the past few years. This is not something that hydrogen can necessarily avoid as they are currently used in electrolyzers and fuel cells. So supply chain strategies will be important to make sure that these materials can continue to be supplied to local manufacturers. There's also ongoing efforts to develop domestic sources of supply for some of the resources identified here, which will help alleviate supply constraints in the future as well. Looking at the supply chain for hydrogen infrastructure, in general, supply chains for infrastructure are less challenging than for electrolyzers and fuel cells, requiring less sort of rare or less available metals and materials. Most hydrogen pipelines in the US are developed or owned by merchant hydrogen producers. Some of the big players are listed here: Air Liquide, Lind, Air Products. And so, these are the types of companies that have experience in developing and operating hydrogen pipelines today. However, pipeline companies such as Williams or other midstream developers and operators of pipeline projects meant for other commodities like natural gas, are also fully capable of developing these types of pipelines as well. It's also worth pointing out that some of the hydrogen infrastructure that was identified earlier in the presentation, such as liquefaction stations, have not necessarily been commercially developed at the scale that could be required for large scale applications of hydrogen as a tool for decarbonization. We talked about liquefaction stations getting up to $200,000 or 200,000 kilograms per day in terms of size. That's a relatively large jump up from the current commercially available options, which generally max out around 70,000 kilograms a day. So important to develop more technological know-how and expertise in these types of auxiliary infrastructure that will be extremely important, as was pointed out, to move hydrogen around at scale in the economy. Similarly, things like moving liquid hydrogen across the ocean are also still being developed. The world's first liquefied hydrogen carrier made its first delivery just earlier this year, and so now this isn't as connected to Connecticut's own efforts to develop this infrastructure, perhaps, but in terms of a global effort to develop hydrogen as a traded commodity and tool for decarbonization, there's still some developments that need to be made. So I'll pause here for questions and discussion. I identified a couple of questions that we're interested in hearing from you all, both in terms of your response to this presentation and just general thoughts that you may have on the questions of safety and supply chain constraints for hydrogen infrastructure and hydrogen equipment. I already gave a quick overview of sort of our next steps from here in terms of incorporating the additional cost of hydrogen infrastructure into the ongoing analysis on hydrogen prices and how that intersects with supply and demand of hydrogen in Connecticut. But I'm happy to go into more detail about that as well if anyone's interested.
Yeah, Colin, when it comes to pipelines, the big difficulty is permits. Is that part of the discussion?
That was touched on at the last working group, John. And you're right, it is a very big concern. The best kind of, I guess, solution to that is to potentially take advantage of rights of way for existing natural gas pipelines, which is already not a perfect solution. There's some rights of way that are specific to a specific, are concentrated on a specific commodity. So a right of way for a natural gas pipeline might not actually be applicable to a hydrogen pipeline, but yes, getting those permits established is one of the most challenging components of developing infrastructure on that scale, and will require a lot of coordination with local communities to make sure they're involved in the process, understanding and getting their buy-in if the pipeline is going through their community or nearby their community, so that these permits and public buy-in can be sort of more effectively developed in a way that's beneficial for everyone involved.
Thanks.
Sam?
Thank you. A couple just thoughts on this, Colin. In terms of the various possible end uses, amongst them has been, but has been in the far right column, which is blending into existing pipelines. I think we have about 8,400 miles of pipeline in Connecticut. Is there any analysis of how much has been upgraded to meet the standards for hydrogen that you mentioned, and also the cost analysis, if it's comparable to gas pipelines or not, and what those costs look like compared to the electrification option. And I've forwarded you some documents from New York that I hope will be helpful on the cost of pipeline replacement there, which can be anywhere from 1 million to 8 million plus per mile, depending on the location and the density. And then secondly, I think in terms of safety procedures, it's really important to include community engagement and environmental justice issues alongside that. I think, you know, we know that a lot of fossil fuel infrastructure has been disproportionately cited in environmental justice communities, and I think it's important not to repeat those mistakes of the past in doing this. And so just thinking about what processes need to be in place for community engagement and having the community decide whether they want projects that may you know, have safety concerns in their areas.
That's a really good thing to call out, Sam. Thank you for bringing it up. Yes, I guess we maybe got too used to thinking about environmental justice and safety as like separate components in the sort of use case criteria that we developed. But you're right, they're absolutely intertwined, and community engagement is critical to get any sort of buy-in for a project, but also to make sure that everyone is actually benefiting from any infrastructure that's put into place in order to realize the vision for hydrogen that Connecticut decides is right for its state. To address your other questions, in terms of pipeline, the ability for Connecticut's pipelines to accept blends of hydrogen today, to my knowledge, there hasn't been any analysis on Connecticut's gas system specifically. There have been studies on, I guess, gas systems around Connecticut. Like I know Massachusetts and New York have been doing some work on that front, I believe. However, it's important that because of the way that infrastructure for gas is different from place to place, it's really important to test the blending or use of hydrogen in existing pipelines on the infrastructure in Connecticut directly rather than pulling in assumptions from other places. And so up until like that's done, it's hard to say exactly how much hydrogen could be used in Connecticut's system without major retrofits. It could be as low as 2% by volume. It could be as high as 20% by volume. And these are long processes. I think California just completed like a multi-year study and concluded that like up to 5% by volume was okay in California without any major retrofits, but additional research was still needed to test higher blends. And there are very few places in the world where blends above 20% are considered feasible without major retrofits, both to appliances and to the underlying infrastructure. And then to your question on gas infrastructure, I'd say that for delivery of hydrogen as a gas via pipelines, it's not too different than the delivery of natural gas. I mean, there are different compression requirements. There's different kind of technical specifications for how hydrogen operates versus natural gas. There's different materials that need to be used to safely transport hydrogen across long distances with pipelines without leakage or embrittlement of the infrastructure. But in terms of the overall cost, I think it would be somewhat comparable to transporting natural gas. The biggest difference for hydrogen really is, I'd say, if you need to liquefy it at any point. Hydrogen requires very low temperatures in order to be liquefied, and so that's means additional costs from the electricity that would be required to liquefy hydrogen versus natural gas or other types of gases that you conceivably liquefy in order to make it easier to transport or store. In terms of connection to electrical infrastructure. It's a tricky question. It's a hard one to like compare apples to apples, because for the most part, electrifying buildings doesn't necessarily require additional transport infrastructure or additional electrical infrastructure in the short term. But over the long term, with the increasing load from houses that are switching from electric to or from gas to electric heat, there would need to be additional upgrades in transmission, in substations, in carrying capacity and generation in the region. The cost of that is similar to pipelines, very closely connected to like where you need to put the substation or the new transmission lines or other infrastructure. Highly densely populated urban areas are naturally more expensive. And so I don't really have the ability to speak to a strict cost comparison between the two. That really needs to be part of a broader study that looks at different potential demand scenarios for electricity with high usage of heat pumps and other electric heat options.
Thank you for that. Just quickly, because I know we're over time. I guess the other question to be thinking about is at a blend of 2 to 5%, does it prohibit us from meeting our greenhouse gas reduction targets by, continuing the use of pipelines and the gas system overall over the electrification scenario?
Yeah, so getting 2 to 5% of the carbon out of the gas system with hydrogen would obviously get us nowhere near the climate targets that we need to hit, and that Connecticut has committed to hitting. And so in that sense, hydrogen blending into pipelines is not a complete solution. You would have to find some other way to decarbonize the rest of the gas, which is, I'm sure we're all aware, a very challenging proposition, and in many ways equally the feasibility of that is something that would also have to be studied in more detail. I would say it's pretty clear that decarbonizing the current level of natural gas use with hydrogen alone is impossible without significant retrofits on the system. I hope that answered your question. And I know we are over time, so I'm happy to end it here. If anyone has any other questions or follow-up thoughts, feel free to send comments to me directly or through the public comment process. And then these slides will be loaded up on the Connecticut Green Bank website soon for you to download as well.
Okay.
Thank you.
Thank you.
Thank you.
Thank you.